Welcome back, students. So today we will have a small revision of the number system, the different kinds of numbers, their definitions, their understanding, some of their uses. Okay, now this is something that you must have been studying for a long time, because these are generally things that are taught in the lower standards. Okay, but then it's not that they are not of any use when you reach 8th, 9th and 10th levels, or for that matter even beyond that. Okay, so it will be a bit of a revision of those different kinds of numbers, and I'll tell you some things where children usually have a little difficulty in terms of plotting on the number line. So we will discuss number line also, which is the real number line. Okay, and so on and so forth. So let us start with some of the very basic things first. We have something which is known as natural numbers. Okay, so we are all aware natural numbers, they start from 1. So you have 1, 2, 3, 4 and so on. Okay, now they go up to infinity because you cannot really have limited number of natural numbers. It goes beyond something that you can count. Okay, so the important point to remember here is that they start from 1, okay, not from 0. And you must also observe that there are no negative numbers over here, as well as there are no fractional numbers here or decimals. Okay, so this is what you have to keep in mind with regards to the natural numbers. Then comes naturally the whole numbers. Okay, now this natural numbers, they are denoted with the capital letter N. Whole numbers, they are denoted with capital letter W. Okay, and where do the whole numbers start? They start from 0. Okay, so 0, 1, 2, 3, 4 and so on. Okay, so as you can see that there is a very small difference between natural numbers and whole numbers, and that only difference is this number. Presence of 0 is there in whole numbers, whereas 0 is not present in the natural numbers. Okay, rest everything you can see is exactly similar to natural numbers. Okay, so this is the next one. And then obviously you have let's say for example rational numbers, or before rational numbers we will discuss integers. Okay, so these are some things that are very very popular. Okay, you can call them integers or you can call them integer numbers and so on and so forth. So you see, the difference between integers and your natural or whole numbers is that they have the negative numbers also included. Okay, so just like you start from a particular number and then you go on up to infinity in these two cases. In integers case, it goes to infinity on either sides. Okay, so it's like let's have 0 in between. Okay, and then obviously to the right side of 0 you will have numbers like 1, 2, 3 and so on, whereas on the left hand side you will also have numbers like -1, then you will have -2, then you will have -3 and so on. Okay, so it is like this side also you go up to negative infinity, and this side also you go up to infinity. Okay, so there's nothing like negative infinity and positive infinity. It only indicates that it is going up to somewhere where you cannot really count up to. Okay, so these are like infinite numbers. Okay, so whenever you talk about integers, and the difference between integers and natural or whole numbers is the presence of these negative numbers also. But you must remember that integers also, like whole numbers and natural numbers, do not have any fractions or decimal numbers in them. Okay, so this is and yes, certainly you have capital Z to denote integers, or you also have a letter capital I to denote integers. And you must also remember that in some cases the negative integers are represented with a minus sign along with Z. Okay, and all the positive integers, they are represented with a plus Z sign. So whenever somebody in number system or in questions related to sets if they use this plus z and minus z, you now know what they mean. Okay, so these three were the very basic ones. Now let us move to something that creates a little bit of a problem in terms of memorizing them. Okay, so let's see. We have something which is known as rational numbers. Okay, you have rational numbers, but they are not so easy to understand. This couple of rational and irrational numbers, they are not so easy to understand. Okay, so you have we'll take a number of examples to understand what rational numbers are. If you go by the definition in most of the 8th and 9th books, you will find that all rational numbers, they can be expressed in p by q form, where q cannot be 0. Okay, so p by q form, so basically it is a fractional form. Okay, so let's see, let's take some examples. So let's say so here q is not equal to 0. So because if you have a fraction in which the denominator is 0, that goes up to infinity, so that is not something that we want here. So rational numbers, let's take some examples. So is 1 a rational number? Yes, 1 is a rational number because 1 can be expressed as 1 upon 1. Similarly, 2 can be written as 2 upon 1, so that's also a rational number. 3 can be written as 3 upon 1, so that is also a rational number. Similarly, you have, let's say for example, 2 upon 3. Is this a rational number? Yes, it is a rational number because it can be expressed in p by q form. Now, this is not the only definition that works. Okay, because you see, you also have, along with this p by q definition that you also have certain different types of numbers that come. Let's say for example, let me take square root of 25. Okay, so right now I'm discussing rational numbers, because once you understand rational numbers, all aspects of rational numbers, then you will be very easily be able to understand what irrational numbers are. Okay, so anything which is not rational will certainly become irrational. So let's say we have a number root 25. So this root 25 is naturally square root 25, because whenever we don't write a number 2 here, it automatically means it's a 2. Okay, so square root of 25. Now, is this a rational number? We all know that root 25 can be written as root of 5 into 5. So we pair 5 and 1 5 comes out of it. Okay, so root 25, which was my original number, has now become 5. So the value has not changed. I have only been able to express this root 25 which was looking like a rather complex number. Complex not exactly by definition, complex means difficult looking number it was. So I have segregated that and brought that into a form which we all like. So it's like a simple number without the root sign. So we have 5, which can certainly be written as 5 upon 1. So this is p by q form, where p and q are integers and then q is not equal to 0. So is root 25 a rational number? Yes, root 25 is a rational number. Now, so this is one aspect of it. Now you see, there are numbers like let's say for example, under root of 3 or under root of 5. You see, we will try and compare such root numbers with a number that we already discussed. So I just now discussed square root of 25, and I said I found out that this was a rational number. How come this became a rational number, or how did you judge that this was a rational number? Because you could see that the number which is there under the under root sign is a perfect square, which actually resulted in the number 5 coming out of it. Okay, so it became a rational number. Okay, and it fitted the definition also. But can you do the same things here? No. The answer is no, because you can simply see that these two numbers that are there in the under root sign, they are not perfect squares. So the square root of any non-perfect square is not going to give you a rational number. These are going to be irrational numbers. Okay, these are going to be irrational numbers. Okay, so what is one different thing that you have learned with regards to rational numbers apart from this definition P by Q? It is that any square root of a non-perfect square number is not going to give you a rational number. It is going to give you an irrational number. Okay, and if you want, you can check also by doing by actually finding out the square root of 5. You will see that it will actually give you a decimal number which will neither terminate, that means neither end, nor it will repeat. Okay, so it will be a non-terminating and non-repeating decimal, which is always an irrational number. Okay, so now slowly we are going from the definition of rational numbers, and now we are stepping into irrational number. So how do you distinguish between an irrational number? How do you judge whether a number is an irrational number or not? So let us write some details about irrational numbers also. So let's see, let's say that you have an irrational number. So an irrational number. So the easiest way to find out about irrational numbers are all, so I'm writing the first point here, all non-terminating comma non-repeating decimals are irrational. So that is the very first thing that you should remember about irrational numbers. The second thing, now these are small points to keep in mind, because whenever you come across an irrational number, they will more or less fit into these two criterias. Okay, so square root of any non-perfect square, which is exactly what we discussed just now by taking examples of root 3, root 5, you can have root 7, you can have root 17, you can have root 13. So what are all these numbers? These numbers are square roots of non-perfect squares. Had they been perfect square, then only one number would have come out, and then we could have written it in the P by Q form. Okay, so that would have become a rational number. So these two definitions, and similarly you can have the cube roots of any non-perfect cube number, and so on and so forth. So that is already there. Now keep look at these two, keep these 2 points in mind, because we are now going to discuss some examples which will help you understand these 2 points. Okay, the second point is already understood. I will take up the first point with regards to using examples to judge. Let's say we have a number 1.5. Okay, now we are going to understand these two terms, non-terminating and non-repeating. Okay, now terminating means ending. Okay, so if somebody writes a number 1.5, now that is certainly a decimal number. We are talking about decimal numbers here. So 1.5 is a decimal number, but the question comes, is it a terminating decimal or a non-terminating? So you can see that it has ended at one place of decimal. So it's not like 1.5, 2, 3, 1, 6, 4, 2, 5, 8, 3. So a number like this and a number like this, what is the similarity between them? The similarity is that both are decimal numbers. But what's the difference? Difference is the important point here. Difference is, as is very clearly visible, that this is a terminating decimal which has terminated at the first place of decimal with a digit 5. Whereas this is non-terminating because it is not ending, it is continuing. You can see that there are so many different digits or decimal places after the decimal. Okay, and it still continues, it has still not ended. So this is an example of a non-terminating decimal. Now come to the word non-repeating. Okay, take that example again. 1.555, something like this. Whereas again you have 1.523164258 and so on. So now again when you compare these two numbers, the difference will be, you can see that all the numbers or all the digits after the decimal place, they are repeating. It's in fact number 5 is repeating all the time. So this is a repeating decimal, whereas this is not a repeating decimal, because there is no number, no sequence which is getting repeated. You can see a number 5 here and 5 here also, but you can't say that it is repeating, because all these numbers, all these digits are in tandem order. There is no particular sequence. Okay, so this is an example of a non-repeating decimal. So can I say that this is an example of non-terminating and non-repeating decimal also? Answer would be yes, because it is neither ending, neither it is terminating, nor it is repeating. Okay, so all such numbers are belonging to the category of irrational numbers. And in fact, if you take a look at the second point in detail after this lecture, you can try this out. You can try out root 13, root 17, root 23, and so on and so forth. If you will actually try to find out their roots in decimals, you will never get a terminating decimal or a repeating decimal. You will always get a number like this, which will neither be terminating nor be repeating, and therefore they all come under the category of irrational numbers. Okay, please remember this very, very clearly. This is the crux of irrational numbers. Now, when we have discussed rational and irrational also, now comes let me just give you an idea of what is it that we are all studying over here. You see, when you talk about the number line, you see this is a number line with arrows drawn on both ends. So in the center somewhere you have 0, then you show 1, then you show 2, and so on. And similarly to the left side you show this. This is the general tendency or the general way in which a real number line is drawn. But this certainly does not mean that these are the only numbers present on the real number line. You most often people forget to use the word real number line. Real number line. Usually people say number line. Okay, they forget to use the word real, because all the numbers present on this line, they are real. None of the numbers are imaginary. And the reason why I am taking this up just now is because we discussed natural numbers, we discussed whole numbers, we discussed integers, we discussed rational numbers, and so on. So you see, where are all these numbers going to be? Are these numbers there on this real number line or not? We can easily see. You can see 0 is a whole number. So a whole number is present here. 1 is a whole number. 2 is a whole number. 1 and 2 and 0 and -1, these are all integers also. Natural numbers 1, 2, 3, 4, these are all natural numbers. Then let's talk about Q, which is a rational number. So what is an example of a rational number? 1.5 is a rational number. Why? Because you see 1.5 can be written as 3 upon 2. So isn't it P by Q form? Yes, it is P by Q form where Q is not equal to 0. So 1.5 is a rational number. It's a rational number. Why? Because it can be expressed in P by Q form. Also, you can use that definition of irrational number that I gave you to check out whether this fits in that category or not. Is it non-repeating? Is it terminating? Or is it non-terminating? So what is it? You can see that it is 1.5. So the decimal place has ended, terminated. So this is a terminating decimal. Terminating decimal is a rational number. Had it been non-terminating, had it continued without repeating the numbers or the digits, then it would have become an irrational number, and that too would have been plotted on the same number line. Because all these numbers they belong to the category of real numbers. Okay, real numbers. Okay, so all are going to be plotted here only, although you certainly cannot show all of them here. If you want, you can show 1.5 here, but if somebody wants you to show 1.0005, can you show it here manually? No, that's a difficult thing to do. So the essence here is that a real number line will have a natural number, whole number, integers, positive, negative, rational, irrational. All the numbers are going to be present. Do you want to see let's say root 25? Root 25 is 5. So is 5 not present on the number line? It is. Similarly, root of 17. If you find this out, it will come out to be 4 point something. So is 4 point something not present here on the number line? It is. So all these numbers belong to that category of real number line. So what is that number which cannot be plotted on this real number line? So that certainly is the imaginary number. So these numbers, let me discuss that also. You have imaginary numbers. Now these numbers have a complex part also. In 11th standard you study that a real part and an imaginary part they have. So what are these? These numbers cannot be plotted on the real number line, because they are not real numbers, they are imaginary numbers. They cannot be plotted on the real number line. And here is an example. Let's say we have root of minus 25, square root of minus 25. So can you think of a number which when multiplied by itself gives you minus 25? See, if you do 5 into 5, that is going to give you 25 with a plus sign. If you do minus 5 into minus 5, it will give you minus minus plus 25 again. You certainly cannot do this. You cannot do 5 into minus 5, because then you are not actually multiplying the same numbers, because for square root you need to have the same numbers. So that is why this cannot be plotted on the real number line. This has an imaginary part also that will be plotted on the non-real number line, or the imaginary concept will be there. So this is as far as this is concerned. Now going to the two other numbers which certainly children don't tend to remember, although this is something that they usually remember. A prime number. Okay, a prime number. So what is a prime number? A prime number is a number which is divisible by 1 and itself. Okay, so what are prime numbers? Prime numbers are those numbers which are divisible by only 1 and itself or themselves. Okay, so let's say take an example. If I take an example 4, okay, just take an example 4. So is it divisible by 1? Yes, it is divisible by 1. Is it divisible by itself? Yes, 4 can divide 4 itself. Every number can be divided by itself. But there are other numbers also which can divide 4. For example, 2. 2 can also divide 4. So look at the definition. Prime numbers are only, so the word here that is missing is only. Please remember this, children. Only divisible by, so let me just show you this up clearly. Only divisible by 1 and itself. Okay, so if 2 is dividing, if a third number, any third number is dividing our number, so then that is not a prime number. That's not a prime number. Okay, now look at 5. 1 can divide 5, 5 can divide itself. Are there any other numbers apart from 1 and 5 which can divide 5? No. So 5 becomes a prime number. Similarly, 7 is a prime number, 13 is a prime number, 17 is a prime number, and so on and so forth. Okay, so prime numbers, usually you tend to remember. It is actually co-prime that you don't remember. Okay, so let's discuss about co-prime numbers. Okay, this term is not so popularly used, but then whenever it comes, you must relate it with the prime numbers. So co-prime numbers. So what are these co-prime numbers? You see, co-prime numbers are those numbers which have no other common factor than 1. Now let us understand co-prime. When we were discussing prime numbers, they were individual numbers. Okay, it was only one number. So for example, if we chose 7 is an individual number. It doesn't have to be, clubbed with 9. Then only we will say that 7 and 9 are prime numbers. No, 7 is a prime number individually. 9 is a prime number individually. But whenever we talk about co-prime numbers, then we are talking about pairs. Okay, so there are two numbers. So the first thing that you have to remember is two numbers. So whenever we are talking about co-prime numbers, then we are talking about two numbers together. Okay. Now, what is the definition? Those two numbers should have no other common factor than 1. So let us take examples. Suppose I take let's say 5 and I take 15. Let's take an example. Okay, so because I have to take two numbers, so I have taken two numbers. Now let us see what are all the factors of 5. 5 has 1 as factor, then 5 has let's say, yes, only 5. 1 and 5 are the factors of 5. When we talk about 15, we have 1 as the factor, we have 3 as the factor because 3 5s are 15, we have 5 as the factor, we have 15 as the factor. Okay, so look at these two numbers. When will these two numbers be called co-prime numbers? When and if they have no other common factor than 1. Now you see, 1 is a common factor here because 1 is a factor of this number also, 1 is a factor of this number also. But is 1 the only common factor for these two numbers? No. I can easily see that there is another number 5 also which is appearing as a factor of both these numbers. So this definition does not hold true for these two numbers. Therefore, they are not co-prime numbers. Okay, this is an example of numbers which are not co-prime. Now we'll take an example of two numbers which are co-prime. So let's take an example, an easy example, 3 and 5. Okay, now what are the factors of 3? 1 and the number 3 itself. Similarly for number 5, I have 1 and 5. You can easily see that 1 is the only common factor between these two numbers, and therefore these two numbers can be called as co-prime numbers. Okay, this is the concept of co-prime numbers, but there is an even more important thing about these which people usually do not remember at all. If you are not studying this chapter, then it is quite probable that you will not have this point in mind, and that point is that these two individual numbers which are being called co-prime numbers, they may not be individually prime numbers. Okay, so it's not necessary, although in this case you can see that 3 is a prime number, 5 is also a prime number individually. Let's talk about only 3. Is 3 a prime number? Yes, 3 is a prime number. Let's talk only about 5. Is 5 a prime number? Yes, 5 is a prime number. So they are individually prime numbers also, and when we talk about them together, they are co-prime numbers also, but that is not always the case. So we will take up an example where the individual numbers are not prime, but when you put them together, they become co-prime. So let's take an example of 2 and 15. Now, my purpose here is to understand that if two numbers are given and we have to check whether they are co-prime, then this should be the definition. Only one should be their common factor. No other number should be a factor of both these numbers. But along with that, you should also remember that it's not necessary that both these numbers individually should also be prime. No, that is not a criteria. So let us see. 2 has 1 as a factor and 2 as a factor. 15 has 1 as a factor, 3 as a factor, 5 as a factor, and 15 itself as a factor. So what is the common factor? Only 1 is the common factor. No other number is getting repeated in both. Okay, so it fits the criteria of co-prime. So 2 and 5, they are co-prime. And have a look at them individually also. 2 is a prime number, but 15 is not a prime number, because 15 can be divided by other numbers also, like 3 and 5. Okay, so the important point to remember here is that co-prime numbers individually may not be prime, both of them. Okay, any one of them may not be prime. Okay, so this is what I wanted to tell you. Now comes the last part in this discussion, and that is something which most of the people might not even have heard. So it is this, what we call them as twin prime numbers. Okay, twin prime numbers. So what are twin prime numbers? So twin, again, it means two numbers will be there. So what are these twin prime numbers? Please remember the difference, the definition, that the difference between the numbers should be 2, and the next point is the number themselves should be prime. Should be prime. So when we are talking about twin prime numbers, we are talking about two numbers. Those two numbers should themselves be prime. So let's take an example of 3 and 5. The easiest example. Is 3 a prime? Yes, 3 is a prime. Is 5 a prime? Yes, 5 is also a prime. What is the difference between these two prime numbers? The difference is 2. 5 minus 3 is 2. Therefore, 3 and 5, they are coming under the category of twin prime numbers. So can you think of any other number which is which are twin prime? So 17 and 19. 19 minus 17, the difference is 2 again, and these are individually prime numbers. So these are also going to come under the category of twin prime numbers. Similarly, you can have 41, 43 and so on and so forth. Okay, so children, I hope you have learnt a lot from this particular lecture, because even we as teachers sometimes tend to not keep some of these points in mind, because not all of these things are taught at all the levels. But then in mathematics, we all usually understand that you can come across these numbers anytime. You can come across these concepts anytime, any class, any standard. Okay, so I hope that you will go through this lecture in entirety, and you will certainly have a much better outlook of the number system. Thank you.